So hi everyone, welcome to this lectures. So this is a course about ordinary differential equations. So between Le Havre Normandie University and the Hudson School of Mathematics. And so we have also some participants from the University of Marrakesh in Morocco. All right, so my name is Benjamin Ambrosio and I will be your professor for this course. So, all right, this is the most important slide of the course. So the whole lectures, all the lectures will deal with this equation right here. All right, so you have the derivative of u. So u is the unknown and it satisfies an equation. That's why we call it differential equation. So ordinary, why do we say ordinary, is by contrast with partial derivative. So there are partial differential equations which involve more than one variable, typically the time and the space, while here typically there's only one variable, the time. Okay, so usually it's not necessarily the time, but usually it's the time, and the derivative here is with respect with the time, t. Okay, then you have a function, and you apply this function to your unknown. So the whole course is about this thing. All right, and so as a general fact, f will be a function, a regular function usually, from r to the m into r to the m. That's clear? If you have any questions, just ask me. You can ask the language that you want. Not Moroccan, because I don't understand, but that's okay. All right, then what? So I already said that, all right? I do have some notes which are very close to that. They are in good shape. So you can write, but I can give you also the notes, and I can give you also the slides. All right, so I'm going to move on, right? I will give you the slides, no, don't worry, okay? Okay, so before to get into the sorry, oh no, so before going into the details, this is the outline of the course. Maybe some of you have already read that. So there are 3 chapters. First, it's the general introduction, which is much more than an introduction. We will discuss a lot of examples. You will do some exercise by yourself, and we'll see through the examples a lot of key concepts that we will review after, some of which, because when we will do examples, we will see a lot of things. All right. So this will take us 9 hours. So 3 times 3 lectures. All right. And then we will go through the theoretical results. Those are more so proofs, existence and uniqueness of the solutions. And then the chapter 3, we will deal with some details about steady states, stability, and local dynamics. All right. Okay, so today we start with the first chapter. Okay, then there are 14 items. Hopefully today we will reach point 4 or 5. Okay, I think we cannot do everything, but okay, this will take us the 3 lectures, and in the third lectures, I will assign you the projects. I will give you the projects, right? Then you will have, let's say, 2 weeks to decide how which project you choose, and then you will start to work on the project. All right, so let's go to the first point. It's Newton's equation. So Newton's equation are ordinary differential equations, all right? So basically, when you have a particle, it moves under some forces, and the trajectory of the particle is ruled by this law. So m is a constant, it's the mass, then you have the x, and then you take 2 derivatives with respect to the time. And here you have all the forces that apply on your particle. All right. And so we will start this course with an exercise which are basic maths. These are basic maths, but behind we will start to see some key concepts of the course. All right. So you can write down this equation because we will need it for the exercise. So the equation is mx. You take the second order derivative of x, then you have a f. F will be given in the exercise, and you apply it to x. And so I propose you the following exercise, which is written here. So first, so I ask you to, by writing y equals x prime, to rewrite the equation in a way that only the derivative of order 1 appears. All right, that's the first point. Okay. Okay, so I'll let you think about this exercise and I come back after. So what I'm looking for is to compute the exact solution of this equation. So I'm going to use the fact that y prime equals 1 divided by m times f of x, which gives So f of x is 0, 0 minus mg. And for the last, okay. And so now I'm going to use the fact that the initial conditions are given. So if y1 of prime, y1 prime is 0, which this means that y1 of t is a constant, and I know that y1 of 0 is also 0. This gives me that y1 of t equals 0, y2 of t equals a constant, but y2 of 0 is k2, right? And then y3 of t, by integrating this equation here between 0, no, not this one, sorry. This is not, there's a mistake here. This is not 0, right? Is a t. Sorry about that. And so this gives you, yeah, and you're right, it's minus g. Thank you. All right, and so this gives me minus gt plus k3. All right. Okay, then I can come back and I will find, thanks to these equations, I will find my x1, x2, and x3 by integrating these equations. So I will get x1 of t is 0. X2 of t is k2 times t plus 0, and x3 of t will be k3 of t minus gt squared divided by 2. All right, so this is the question 2, and for the question 3, from here I can express t as a function of x2, and then I plug it into the last equation, and I find that x3 of x2 equals, so sorry, because it's k2, all right, yeah, k3 divided by k2 times x2 minus g divided by 2k2 square and x2 square, which is a parabola. And this is a well-known fact, all right? That when a particle is just ruled by the gravitation, this gives a parabola. And so I can draw it. If I draw it, I will have something like that. So here I will have 2 divided by G, and here I will have 1 divided by G. All right, is there any questions? Okay, so let's move on to another example. So I made this plot, all right? I made this plot. I just plotted the, it's the function. Here you have x3 as a function of x2. So x3 equals x2 minus g divided by 2, x2 to the square, where I took g to be 10, which is a Roth approximation. That's why you have 0.2 here. So this is easy computations, but you have seen a lot of things in this simple example. All right. So I will come back to that. Okay, another example is given by electrical laws. All right, so if you have this circuit, if you have a potential here, which I call U, and then you have 3 components: a resistor, an inductor, and a capacitor. And I put it in parallel. So now you have an electric current which flows across the circuit, and it divides into these 3 paths. And so by Kirchhoff law, you have that the intensity, the current that flows through this wire equals these 3 currents, right? Okay, this is Kirchhoff's law, or in French, la loi des nœuds, right? All right, now each of these components has his own equation with respect to the U, and it writes like that. So the current here, which goes through the resistor, this is given by the Ohm law. So IR, so you have U equals RI, or IR equals U divided by R. So the inductance, it's like this component as it's a spiral, you know, and so this means that the intensity here is governed by this law. So my IL here is given by this law. So it's U divided by L. So L is the inductance. And finally, you have the capacitor. So the capacitor is basically, you have a space here, and when the current goes through that, it increases the voltage here. So the law is IC equals C U prime. Okay, now I can okay, I'll let you just do this computation. You can take the derivative here of this equation here. Oh, you don't see. Okay, they see, but you don't see. So the first equation, if you derivate, you take the derivative, so you will have the I prime equals IR prime plus IL prime plus IC prime. And if you do that, you get this. So you just here, you know, so U prime divided by R comes from this. All right, so this is okay. All right. Okay, so now you get the exercise 2. Again, you can rewrite this equation as an order 1 equation. And if you assume that I prime is a constant, I'm going to ask you to compute the stationary solution. So a stationary solution is a solution that don't move. It doesn't move. So that means that if it doesn't move, it's just stays where it is. And this means that when you take the derivative with respect to time, you have 0. That's a stationary solution. All right, so I let you do that. So this is the solution of exercise 2. So you have to solve this equation. So if you set U prime equals V, you obtain this equation. And then stationary solutions are obtained by setting U prime equals V prime equals 0. And then you obtain that the stationary solution is given by U star V star equals KL and 0. So we are now dealing with the point 3. Oh no, before going to the point 3, this is the picture. This picture that you see is when I take I prime. In this case, it's not constant, it's a periodic solution, which is more realistic. Usually you have a AC current, which is a periodic current. And we could solve exactly those equations, but this is not the point. Okay, we'll get back to that after. So next, the example 3. So it's a classical example of radioactivity. So you have a nucleus that emits some particles, and so it loses quantity. And so there is an equation for that, is that the quantity of matter in the nucleus follows this equation. and where lambda is the rate of disintegration per unit of time. All right. And so, yeah, you can just write equation 1.6. And so I asked you to compute this solution. This is straightforward. So, like, what's the solution of that? You know? So the solution here of equation 1.6 is given by n0 exponential minus lambda t. All right. It's classical. It's okay. I can move on. All right. So okay. This is more complicated. Okay, Hodgkin-Huxley equations. So Hodgkin and Huxley were two physicists from University of Cambridge, and they worked on the giant axon of the squid. You know this animal? So they were doing experiences on the axon, the nerve of this animal. All right. So this is their paper from 1952. So it concludes a series of papers. You know that in the membrane of a cell, there is ionic currents that flows through the membrane. That's how your body works. All right. And so they were working on the cell of this animal, and the basic idea of their work is to say that the cell membrane acts as these circuits. So they say that the membrane of the cell acts like a capacitor, and then there are ionic fluxes, potassium and sodium mainly in this case, that are currents. Okay, and they will write an equation based on this circuit. We can have a look. But if I do that, no, you cannot see it. All right, so it's not worth. So Okay. Okay. And so they came with this equation. So the first equation, here you have the voltage. So here, this is like the previous exercise. You have the capacitance and the voltage. And CUT is equal to a current. So this is the Kirchhoff law. All right. If you write the Kirchhoff law, it's the same thing as we did in the previous exercise. So if you write the Kirchhoff law on the circuit, electric circuit that was drawn before, you get that the current divides into the current of the capacitance IR, which is equal to that, plus this ionic currents. So this is the Kirchhoff law. And here, what's that? It's like the Ohm law. You don't see the first equation here. When you look at here, G N A M to the cube H E N I minus V. This is the Ohm law. This is the Ohm law. But here, the conductance is not a constant, it's this function, right? So let me explain this better for you. These three terms are analog to the Ohm law. You have a voltage and you have the conductance, but one of the assumptions of the model of Hodgkin and Huxley is that there are some conductance, some gates that open and close. They open and close. So it's not a constant like in the Ohm law, but they can open or close. And the opening and closing are given by the three other equations.